Sonalker, and I am a data science consultant at Capgemini Invent. And today I'm going to be talking about a project that we worked with a luxury retailer on in the area of demand forecasting. And following my presentation, two of my colleagues, Scott and Kareem, will talk about a similar implementation we did internally and how we went about it. So I'll just start off with giving you a bit of a background on the problem statements of what we're trying to solve there, the challenges that were industry specific or company specific that we faced, a couple tips that really helped us get along the way, and finally exactly what we built with the luxury retailer. So we were working with the data science team at this particular luxury retailer, where we were trying to help them with their demand forecasting for the 4 different collections that they release within the year, where the merchandisers, who were our end users, conduct the buy for these different collections that are released 4 times in the year. So by that I mean for each collection, there are thousands of products within it, where the merchandisers decide how many of a particular t-shirt will they make available on their e-com platform or their brick and mortar store. And at the time, they did not have a data-driven approach to their seasonal buy. So in addition to not having a data-driven approach, they did not have basically a central place where they could access, images or information from their past collections, so that they could kind of speed up the process of their buy. And lastly, due to inaccurate forecasting, they had lots of unsold stock at the end of the season due to their large supply chain, which led to long lead times, meaning that if they were conducting their buy in January, there were several months between them forecasting how much of the product will they sell on their e-com or their brick and mortar store to actually going on sale on those platforms. So a few things that presented a challenge were the fact that these were completely new products that were released by the design teams, which meant that there was no sales history that you typically have for a demand forecasting project to learn on for the model. Then the second thing being the large lead times in the supply chain meant that things like a marketing push for particular products. So for example, if a particular a bag or a garment was going to end up on a billboard was unknown at the time of prediction. So certain factors that kind of pushed for the item to be, a successful seller were completely unknown when we were trying to forecast for those items. And lastly, the end users had to adapt to a new way of working. So there was a process of learning for them as well. So 2 things that really helped us kind of, make it a success and make kind of any improvements or changes to the initial MVP that was built were the fact that we stuck to an object-oriented programming, which to begin with doesn't sound like a groundbreaking concept, but typically as data scientists, we're really used to going to our Jupyter notebooks, quickly, trying different models out, which did help in the early stages. But when it came to any kind of feature development or any new feature integration that was needed for the end users, it really helped that we had really structured pipelines and stuck to object-oriented ways of programming, and really, helped us to make any changes in the process. The second thing was to kind of remove any dependencies out of any visualization platforms. So not using, Power BI or Tableau, but kind of building a website from scratch, which the end users then just needed a username or a password to log into, and we could kind of make it easily accessible for anyone within the company that then needed access to it outside of our target. So what did we build exactly? So as I said, it was a demand forecasting problem. So in order to tackle the forecasting challenge, we used a gradient boosting algorithm to predict demand of these newly created products, which meant that we needed to learn on a lot of categorical features, such as the color of the item, the type of branding that the item had, the silhouette and things like that, that contributed to the success of that product. So if a newly created product shared these similar features, it learned off of these past products that also had similar features, such as, the same color, if it belonged to the same season as well, helped the model forecast more accurately. The second thing that was really important for the end user was to know if this newly created item visually resembled products from past collections. And knowing how well the product did in the past that looked visually similar helped them also decide how much they were going to buy of this newly created item. So what we did then was to use an image recognition algorithm to show them 150 different visually similar items from past collections in like descending order of similarity, for them to then make a more educated decision on how well the newly created item was sell. As I said, this was also a new way of working for them. Data science was fairly new to them, which meant that there was also an element of them understanding exactly what was going on in the background. So it was really important for us to make the algorithm and the model and the approach really explainable and understandable for the end user. So we helped them do that by showing them exactly what led or how the model made decisions when predicting the forecast for this new item. So was it the color of the item that pushed the number higher? Was it the silhouette? Was it the branding? Was it the material that contributed for the model to be higher or lower? And lastly, making everything really interactive was important, so that the merchants could then enter their decision into the tool. How much did they then in the end, depending on these three points of information, so the forecasted number, the similar images, and the explainability element of the model, help them make the decision. What was there then? What was their end result, or what was their forecast, was then entered into the tool. They could browse items from past collections within that website, and also the model gave them also three different forecast numbers depending on how successful the model believed the product was going to be, so they could select the most appropriate one and make an educated decision. So these were the kind of key elements for the success of the project that we worked on together with the data science team at this particular retailer. But now I'm going to hand over to Scott and Kareem, who are going to present something they built that was fairly similar to what was done with this client internally. So Scott, I'll just hand over to you. I'll stop sharing. Give me just 1 second.
Just as you're doing that, actually, thanks very much for that. But just as you're doing that, I forgot to mention in my rush at the beginning there, we have a Q&A feature as part of the Zoom platform. So during the presentations, if you do have any questions, please do just pop them into the Q&A, and we've left 20 minutes or so to work through them at the time. The other thing to mention, because we have got 3 speakers, if your question relates to someone in particular, please just put a little note on the question that you know which speaker it was for. If not, we'll answer them as a group. So that's it. My piece is definitely said now. I'll get out of the way and hand over to Scott and Kareem if you're happy. Are you good to go, Scott?
Yes, sir. Thank you, David. Thank you very much. And thank you. So first of all, apologies. I'm the reason it started a little bit late. Technical difficulties. I'm blaming Windows, to be honest. Avid Linux user, but okay. So I'm just going to get on. So sharing my screen. Restart the presentation. Okay, we're good to go. You all see my screen? Sorry.
Yes, looks good.
Yeah, sorry. Okay, so essentially, yeah, Fashionista's dream. So as Saudamini said, we have implemented something similar at client, and this is something that we've been doing internally as part of what we call the Python working group. So the Python working group is a place where we can build new products that are going to eventually be taken to market, but also the focus a lot this year has been on teaching people some more advanced Python and bringing people up their ability up. So what we have done, me and Kareem have developed this, and while we've been going through developing it, we've been teaching other people to develop it. So what is it? I hear you asking. So essentially, I'm just going to give you a quick demo. So we've made this web app here, and essentially this is what we're looking at. It's built on Dash. The idea is that clients can come in, they can scrape, they can look at a variety of images, and they can then select these and just see what the similarities are. Now, the images in this folder are all from one particular website, and they're all compared against ones on that particular website. So you might not see the closest similarity, but this is just similarity on one website, not on a whole number of websites. So I'm going to talk to you about how I did this from an engineering point of view, and Kareem is going to talk about the modeling. So, you know, we're both data scientists, but we both get involved in that whole process, which is quite a good skill to have. You know, if that's something you want to do, particularly as consultants, it's useful being at different clients on different sites, etc. So going on, so this is the tech stack that we're looking at. Obviously, we're building it in Python, hosting it on Amazon Web Services. Every data science project is going to use pandas and NumPy. It's not complete without it. Then we're using something called Scrappy for scraping data from the web. The model is built on something called Fast AI, and the dashboard that you've just seen is based on Plotly Dash. So as I say, I'm going to talk to you a bit more about the engineering side, and Kareem is going to talk to you about the model itself. So first off, web scraping. This is where it's all started. So I told you that we use a package called Scrappy, and this is maintained by a company called Scraping Hub, who are not responsible for creating the actual product, but are responsible for maintaining it at the moment. And this is an absolutely fantastic framework. It's really powerful. For any of those who have used Django for web development out there, it's very similar to that and kind of built off the bottom of that, actually. It's basically for building spiders. So you start off by saying, you know, start project, and it creates a whole framework for you to actually start developing your spider. And then in developing this spider, what you need to do is choose a website to look at, identify the relevant elements, CSS and XPaths, to identify what's there. I'm going to go into this in a minute, so if you're thinking, what the hell is he on about, don't worry, it will become clear. Then there's something called the Scrappy shell, which is useful for debugging and finding out exactly what you want to be looking at. So we've got an example of the inspect element and the Scrappy shell here on the right. And one of the really powerful, extra powerful things that Scrappy gives us is we can do data cleaning inside the spider. So we are doing a lot of list comprehensions to clean up the data inside the spider that we're using. And you can also pre-process files such as images. There's something called the image pipeline, which you change in the settings of the framework, in the settings file that the framework actually gives to you. So I'm just going to go back to the internet and make that a bit clearer as to exactly what is going on. So essentially what we've done is we've identified a number of sites. We go into a site, we go to the new arrivals. We're just concentrating on new arrivals because we want to see what the trends are. And the idea is you basically right click an element And what we're trying to do in each page is make the spider go in, and it's trying to take the details out of where this element is and then pass on to the next one, pass on to the next one, and going through. Now, HTML is, very well, it's basically kind of like tree language, very well structured, and CSS gives it that the formatting, and we're actually able to pull out a lot of information through this, and we do this through, like I said, what we call the Scrappy shell. So have a shell just loaded up here. So you basically install it, you type out Scrappy shell, it comes out like this. It's a little bit, for those of you who have used IPython before, which is sort of before there was Jupyter notebooks, everyone would be on IPython. Essentially, this is quite similar. So right, so first thing you're going to do is you're going to fetch the website, just put the command in there. So what that's doing now is it's crawling the website. Next thing you want to do is you want to check that you've got a response. So you do this view response thing. Now this should load up the web page. Now, if you look in my address bar here, it's actually now locally stored as a file. So we have access to the website. In this case, there's actually an error, and the reason for that is that you cannot scrape this one with Scrappy itself, and I will get that back into that in a second. But essentially, what's happened is Scrappy goes in. It gets the response, and then it gives you a text. It's a text-based web scraper. So all that text that you just saw coming down the screen there, that is all text behind the website. So why were we not seeing anything in this example? I've purposely chosen this example for this exact reason. So what's happening is these images that we're looking at, and a lot of the website is actually being served through the through JavaScript. So we see here essentially what we would normally be looking for is to try and get this source of the image, and you see these three ellipses here. Oh, these ellipses, sorry, not three of them. That basically tells me that I can't scrape this site using Scrappy. The reason I've chosen this as an example, because I don't want you to get down a rabbit hole when you're coming to implement this and finding the same difficulty. So if you're in a situation like this, it means you've got to find another website. And so this was one of the things that we did. We were just looking at websites with that. So yeah, that's that. And basically what you would do is you would use list comprehensions to break this list down. Notice it is a list, and break this list down to get all those sources that you actually wanted. So you just have a list of source images. These then feed into your spider, and then it pulls these down. Anyone not familiar with list comprehensions, I highly suggest that would be like my top recommendation for data scientists and Python developers to get into list comprehensions. If you're not yet, they are so helpful. They take your game up another level. So yeah, that's Scrappy. I've just got a couple more things to say on that. So as we said, there's all those strengths to it, but it is text-based, and you can get over the JavaScript issue by using something called Scrappy Splash, but this requires knowledge of another language, and LUA, for rendering those JavaScript images. There are other options as well. You can try and use something like Selenium, which is actually a program for testing websites, for web testers, but you can scrape with that, but it has its limitations as well, and there are other various packages out there, but it's the framework for me, the power of Scrappy that allows that, is the reason for using it. So moving on to the web application that I showed you. So this is built with something called Dash. It's by a company called Plotly, and many of you might be aware of Plotly, interactive HTML-based graphing software, a bit like Matplotlib, but like, in loads better. I don't want to say loads better because it's a different application, but web-based and interactive, etc. So Dash is built on top of Flask, which is a micro framework for web development. I mentioned Django previously. Django is a heavyweight web development thing for people who really know what they're doing. There's a lot of hardcore stuff in there, and it's easy to get lost in the construct of Django. So if you're just starting out, it's best to go with Flask, although you'd be tempted to go with Django because it has all this functionality. And then Flask itself was built on Facebook's React JavaScript, which JavaScript library for lazy loading, essentially, is the primary thing on that, on Facebook, where you're lazy loading your stream. That's essentially where it comes from. So one of the beautiful things about Dash, Plotly Dash, is that you have full integration of HTML, CSS, and JavaScript. You'd have to use these files. The file that the one that you saw actually has a separate CSS file that's serving the CSS. And then, of course, the huge advantage is your full use of Python inside of there. So if you are familiar with using dashboard softwares or BI softwares such as Power BI and Tableau, you can use Python in there, but not fully. And whereas in this case, you can use Python fully. Now, I'm not sort of trying to put those other packages down. That's amazing software, really powerful, but they have their uses. And for this use case, it wasn't appropriate to use to Plotly Dash. So we use to them. So we use Plotly Dash, which is typically for dashboarding. So the main parts of Plotly Dash, just go through those. There's three main parts essentially. First of all, you define your app and instantiate your app by importing Dash and creating your Dash app. You can give the Dash titles, etc. And then the second part is defining your layout of your layout. Okay, so your HTML layout, and in here comes the Dash HTML components and also the Dash core components. So the HTML components are basically HTML divs, images, all the things that you can do in HTML, you can do with Dash HTML components. And then all the interactivity, such as uploading the picture, comes in with what you call Dash core components. And then as well, those core components on themselves are not enough. You have to add some functionality with what the app callback decorator. So essentially that provides the functionality. And for those that are unaware, the decorator is basically just a decorator. You throw a function at a function is the simplest way to put it. So again, I'm going to go to the net and make that a little bit clearer as to what I'm saying. So as I said, we've used Dash in a kind of a non-typical way because we're just showing these images at the moment, but we are hoping to bring in plots, etc., which is really, where Dash's power comes in is the plots, etc. So I just we're going to bring those in with forecastings and all these different things. Okay, so they're going to be built in. So here's an example of a website another Dash site that I'm working on in my spare time. And this is basically a worldwide global coronavirus daily report. So we have a map that you can bring in. We can go between deaths and cases. It's quite interactive. We can look at plots. So here, I said Plotly is quite interactive. So you can actually see these plots in your Jupyter Notebook, for example. We can zoom in. We can download it as a PNG. Do different things. We can unselect items. We can add countries, and so this addition of the countries, for example, this is coming from that app callback that I talked about, where basically we're making callback. And then again, I've got one with news headlines that's pulling data from Google API, and also this. So this is Dash tables, and this is something I didn't mention in the presentation, but this is super powerful. This is HTML tables. You can filter on it and stuff. So we just put less than 1,000. We have all the cases that are less than 1,000. So, Dash is an absolutely really powerful framework. And again, like I say, you can completely make it how you want to make it look by bringing in the CSS, as we've done in both cases. The app that I'm showing you here is about like 300-400 lines longer. It could probably be condensed further, and the CSS behind it is about 300 lines. So you can do a lot with very little. And then also be sure to check out if you're interested, check out the Dash app gallery, because there's lots of different examples of things you can do in there. Some really great stuff, real-time object recognition in there, for example. So back to the presentation. So yeah, just to recap, Dash, really powerful. 3 key steps: defining your app, defining your layout, making your app callbacks. The app callbacks bit is where it's going to get a bit more complicated, but go on that Dash website, some really great tutorials for you to get started. Okay, so once the app's built. What have you got to do next? You need to deploy it. So we're going through this at the moment and getting it fully deployed, and we're using an EC2 instance. So Amazon Web Services is great. There's so many different opportunities out there, tools in there that make it easier and easier for people to do data science. I mean, you can do data science if you don't even know how to do data science in AWS. You know, there's the sort of like the high level where you, as a non-data scientist, can go in and do some object recognition. Then there's the middle layer with things like SageMaker and stuff, which allow for that pure kind of like model development, etc. And then there's like the lower hardcore level, which is software engineer, developer, whatever. And this is sort of the layer that we're deploying it on. Okay, so using shell based. So essentially use an EC2 Linux instance, spin that up in the cloud, and you basically, you know, rather than having like a nice operating system to work off, you just have a shell that's just like this. And what you do in this shell is you build your Python environment using virtual environments, not Anaconda or Conda. Try and refrain from using them. You can use those, but really when it's going to deployment, you want it bare bones. And to get it to bare bones, you need virtual environments, which I believe Conda kind of builds off, but don't quote me on that. One other important thing, and this is super important, one of the most important things I'll say, is that you need to set your debug on your running your server of the app to false, because if you don't and that's set to true, you'll notice that when I am, so for example, here I've got that running. Okay, this is running the Dash app, serving it up, and all these things are coming out, and it will give me error messages and stuff. You really don't want these error messages to be shown when it's live, because that's basically a way in for hackers. So kind of fine if you're just doing it personally and messing around, or they really don't want to do that anyway. But if you're at client side, well, that's, you know, potentially really dangerous. So those parts about the EC2 instance, and essentially, and I'd say anyone kind of new or anyone interested in this sort of stuff, I'd get rid of Windows on your personal software, on your personal laptop, and get Linux installed, because this will really give you an edge up in AWS using these EC2 instances. They do actually have Windows PowerShell and stuff as well. So if you really are a fan of Windows, you can do it through that. So Elastic Beanstalk is the way that we're going to deploy it. So this takes all the headache out of deployment for people who are not so much into the web hosting side of things. So for example, traditionally, the best way I can kind of put it in a way is traditionally you would buy a number of gigs of data off a web server and a hosting package, whereas Beanstalk basically it will allow you to fluctuate up and down depending on use, which can be is a difficult thing to do, but it sorts all this out for you, so it's a great option. And also in the deployment, the front end and the back end, it's best to deploy them separately. You can deploy them at the same in the same app. However, you're going to suffer from speed issues there, where the model's deploying or the model's doing something, data's being collected, and that's not really good. Also really important for CSS grids once you go live, or just CSS. This is using, it allows you to basically, I haven't kind of mentioned and just assume that people would know when I said CSS. So CSS, cascading style sheets, is basically the formatting language of HTML. So HTML says what you've got on the page, and CSS is what tells it what color it is, what position it is, what size it is, all that sort of stuff. And then if you're wondering with a JavaScript, that basically tells, that's kind of like dynamic HTML is the best way I can simplify that. So this is actually using something called CSS grids, which is the latest CSS implementation, not supported by Internet Explorer, but you know what is these days. However, this is a really important point, because you know, with a lot of you know, big organizations, there still sometimes is a dependency on Internet Explorer, so it's something definitely to be aware of when constructing these things. What browser you're going to be showing it through, multiple browsers or just one. And so the model itself as well has been built in SageMaker, which is absolutely fantastic for doing all this stuff, and will actually allow us to deploy the model as well. So without further ado, I'm going to hand you over to Kareem, who's going to talk you through the actual model, get to all that sexy modeling stuff there.
Awesome, Scott. Thanks very much. Scott, can you just let me know if you can hear me?
Yeah, I can, but sorry, I'm just gonna have to. I need to turn my video and mute myself, and I'll put the presentation back on.
Awesome. Cheers. So, hi everyone. My name is Kareem Rodgers. I'm a data scientist at Capgemini Invent, along with Scott and Saudamini. So, going into a bit more detail about the image similarity model, we applied transfer learning to train a convolutional neural network on a public fashion product data set. And this data set is called Deep Fashion. If you jump to the next slide. So Deep Fashion is a data set that was produced on the back of a publication. So we're quite fortunate that this kind of data set already existed. It consisted of 300,000 product images, and it had a variety of the image types. So it had individual product images, it had modeled images, and it also had amateur photos. And it consisted of 47 different product classes. So this ensures that not only do we have a variety of image types, we have quite a variety in different classes and different products. And both of these things are really going to help the model to generalize. And also, because it was produced on the back of a paper, they had already pre-partitioned the data set. So it already had been split into a training, validation, and a test set. And this meant that we didn't have any issues with sampling and ensuring there was a lack of bias for different products and different sets. It was pretty equally sampled, and so we could just go straight ahead and feed that into the model. Jump to the next slide. So in order to produce and train the convolutional neural network, we utilize FastAI. So FastAI is a Python machine learning library that's built on top of PyTorch. For those not aware, PyTorch is Facebook's machine learning framework that they've developed. It's essentially a direct competitor with Keras and TensorFlow, produced by Google. But the great thing about FastAI is that it makes using PyTorch really easy and simple and very intuitive, especially when it comes to transfer learning. So transfer learning is a methodology for really efficient model training and tuning. For those not aware, what you do is you take a pre-trained model and you tune its final layers so that it becomes particularly good at attempting to classify for the problem you're trying to solve. So this model is already good at classifying images, but we're tuning it for our particular set of classes. And what we did is we used ResNet 152 as our pre-trained model. Now, ResNet just describes the architecture of the model, whereas 152 is the number of layers within the deep neural network. So ResNet 152 was trained on ImageNet, which is a really famous benchmarking data set. And ResNet is state of the art at the moment, and it achieves some really kind of amazing performance with image classification on the ImageNet set. So what we did was we took ResNet 152 and we unfroze the second last layer of the deep neural network. And then we trained and adjusted the weights and optimized the weights on that layer to optimize it for our problem, which is attempting to classify different fashion product images. And just wanted to show you a snippet of the code just to show how easy it is. So regardless of how your code is, how your data is structured, for example, our data, we had images in one folder and labels in a text file stored somewhere else. FastAI makes it really easy to collect your data and put it into a single object, which you feed into the model. So here we have an image data bunch, and you can see it's made up of a train, validation, and a test set, and they have their associated labels and their associated path locations. So all you end up doing to apply transfer learning is you call the CNN learner method. You provide it with data, which is the image data bunch you can see above. You specify the model you want to use. In this case, it's ResNet 152. And then you define your metrics. So we have the classic error rate and accuracy to judge it, but also for image recognition, you'll often find people using top K accuracy. In this case, it's top 3 accuracy. So the output of the neural network will be a probability distribution across all the different classes. And if you're trying to solve a problem with lots of classes, you may find that classes are quite similar. Specifically in this problem, you might find that trousers and jeans kind of are quite similar looking to each other. And so what top K accuracy shows is that it it pulls the 3 classes which have the highest probabilities. So for example, if you're trying to predict the genes class, the highest probability may not be genes, but the second highest or the third highest may be genes. And that indicates that your model is still performing, and it's just a facet of the data that it didn't end up being the highest probability. So also I wanted to touch on why we chose ResNet. So ResNet's really good. It's state-of-the-art for image recognition because it eliminates the vanishing gradient problem. This allows for much deeper networks, and the deeper your network, the more abstract the patterns you can pull out of your images, and will enable classification. If we just shuffle on to the next slide, I'll try and cover this in a bit more detail without going into too much depth. So the reason the vanishing gradient problem arrives is because of the use of activation functions within your neural network. So within a network, you will have activation functions at each layer within each node, and the purpose of activation functions are to transform the input to a particular output. An example of an activation function is the sigmoid. So all this does is it takes an input, any number, and it will transform it so that it will be within the range 0 and 1. So the problem comes across with vanishing gradient when you're doing your backpropagation. This is where you're attempting to optimize the network. So you're trying to adjust the weights. So you're enabling the model to classify the correct images. So when you're doing backpropagation, what you're essentially doing is a kind of large derivative multiplication. So I often use this kind of diagram, this little snippet, as a really good reference to help remind me of how it all works with neural networks in general. So if we start at the far end and we have our output, we want to ask the question, how does a change in weight number 5 adjust the total error? And we're going to walk through the derivative now and basically demonstrate how the activation function causes a vanishing gradient. So you can see on the equation on the top right, we have how the derivative of E total with respect to weight number 5. Now, in order to work this out, we essentially step back through every node and every layer and every connection until we get to weight number 5. So firstly, we need to find how E total changes with respect to out 1. We then multiply that to how the change in out 1 changes with respect to net out 1. And then we multiply that by how the change in net out 1 changes with respect to W5. Now, the issue occurs when you're trying to find the derivative of net out 1, because that is where the activation function will sit. So if you refer back to the diagram on the left, you can see sigmoid is already within a very small range, 0 and 1. But as soon as you work out the derivative, you're now even less so. You're in between 0 and 0.25. And so as you can see, you're multiplying these derivatives together. And as soon as you hit an activation function, your derivative is going to be between 0 and 0.25. So if you're trying to find how a weight right at the beginning of the network affects your error, imagine how many times you're going to hit a derivative of an activation function that's just going to reduce the output more and more and more. And so this is how, when you get to your weight at the beginning, you're updating it by a negligible amount because it's just being reduced as you go back and back. So just to finish off, in the next slide, you'll see that the way ResNet overcomes this is it actually just skips the derivative of the activation function altogether. So in this case, you see we have ReLU, it's a different activation function, and we basically pass the output around the derivative of the activation function when we're performing backpropagation. That's at a very high level. Go to the next slide, please. So we managed to achieve around 70% accuracy, which was really good. And just bearing in mind, we weren't really concerned with classifying the images. Our goal was actually to perform image similarity. We wanted to determine which images looked similar to others. And so we used the Annoy methodology. So Annoy was developed by Spotify in order to derive similar songs, so it could kind of advertise similar songs to users. But it's kind of doesn't have many bells and whistles. It's an approximate nearest neighbors methodology with some ability to tune how the clusters and the decision tree is formed. However, because it was developed by Spotify, it's readily scalable, it's super efficient, very fast. And so what you do is from the second last layer in your network, you extract the vector embeddings. So if you can imagine this vector, it's a representation of the image in numerical form. And just before you classify it, you have this vector representation. So what you do is each image is represented by a vector in n-dimensional space. You provide this vector to this approximate nearest neighbor methodology, and it determines which vectors are close to one another in that dimensional space. And so that's how we were able to derive which 5 images, so which 5 different vectors were closest to one another in that space. So if we jump to the next slide. So finally, we just wanted to talk about what our next steps are. So as Scott kind of hinted on, we really want to use this as a trend analysis piece. So for the purposes of this webinar, we've just shown one data source. So that's why we weren't really getting kind of optimal similar images, because you wouldn't have a retailer having the same products on their website. So what we've done, and we've got pretty good results, so we've scraped from large e-commerce websites which store different brands, and we scraped those, and we want to use it as a trend analysis tool. So as we scrape more and more of what's new, new arrivals, we're starting to get a really good idea about which brands are producing similar looking products. And then we can gain insights by kind of looking at the attributes. Are they using different materials, different price points, different patterns, for example? So we're going to be implementing that. Also, we want to ensure that the tool is scalable with respect to the cloud modules that we're using and the web functionality. And finally, as you scrape more data, you want to improve the model's ability to predict and classify. So yeah, that's it. Thanks very much for your time. I guess we're going to take any questions at this point.
We sure are, Kareem, mate. Thank you very much for that. It was really good. Thank you, all of you guys. So if possible, if I could get you to flick your cameras on actually and unmute, we'll do a bit of a quick fire Q&A and see where we go from there. But I think from the attendee perspective and watching you guys give that presentation, it was really nice the way it flowed through, setting the scene, what's the problem, why are we doing this, looking at sort of some of the engineering background, then going into the modeling. So as an overall presentation, it was really nice to take things through from start to finish in that way. So that's cool. If you look at the Q&A section, I'll go through and ask some questions and take answers from different panelists. In terms of the questions, sometimes it is a little bit different. It's a little bit challenging to work out which part of the presentation or who was speaking at that particular time. It can also be sometimes that the answers then become clear as you've gone through the presentation. So if any of the questions you think you've already covered or whatever, we can kind of fire through and skip on from there. So I'm going to jump in first. Question from Jessica Willis. Why did you guys choose Scrappy for the web scraping?
So yeah, there's multiple options, but really it's that powerful of that framework. So when you first get on the in the Scrappy shell, essentially, see if I can remember how to do it off the top of my head. You just got to do like Scrappy start project test. I'm not sure if we're going to put a dash n. No, that's not. Oh, here we go. So yeah, essentially once we do this, it will set up a whole basically framework for our spider. Okay, something like that, create project, and it basically creates a number of directories and files, a settings file and stuff like that, which then allows you to really start building complicated spiders. And then you can bring things, you can bring Selenium into it, you can bring Beautiful Soup into it, you can bring anything you want into it, right? Whereas with the other things you don't bring Scrappy into them, you bring Scrappy into that. So yeah, it's just a super powerful framework, and whatever you can do in Scrappy you could build yourself with just HTML requests and various things. But it's the power of Python. Other people, there's such a strong community out there, and we build these products and we use each other's products. So yeah, that's essentially why, just the power of it. It's really is powerful. I really highly recommend people get involved with that.
Perfect. That kind of links in actually to another question that we'd had from Ayadua. Again, it was actually a question for you, Scott, and he was talking about, does Scrappy have an edge in terms of functionality when compared to Beautiful Soup? But what you're essentially saying there is you can layer it all on top of each other and get the benefits of everything.
Yeah, definitely. And then there's that, as I said, Scrappy is a text-based as well. So and HTML is like beautiful soups like HTML and stuff, right, as well. But so the one limitation, given these two questions, one limitation of Scrappy is the fact that you saw with that Burton website, they're bringing in the JavaScript, but it's not really a limitation. You just have to use another Scrappy module, which is Scrappy Splash, which is slightly more complicated because it does require you to learn LUA or LA. So yeah, but you can get past that limitation, which is absolutely great.
Okay, fantastic. In terms of the first couple of questions at the top of the list there from Hamad, what about the different payment platforms for seamless checkout for consumers? If I'm honest, I'm not sure what part of the presentation that was particularly linked to. Does that make sense to any of you guys, or is it best to sort of move on a bit from that one? What about different payment platforms for seamless checkout for consumers?
I mean, the solution that was implemented at client side was more client facing rather than consumer facing. So I'm not too sure.
Okay, cool. So we'll flick forward for a bit for that one. Top question there from Adam Tomlin is probably a question for you, Kareem. What are the benefits of applying transfer learning instead of training all of the layers in a neural network? And equally, if that was for someone else, by all means, anyone jump in.
Yes. So the interesting thing about transfer learning is you essentially reduce the amount of time to train a model, and you may end up with an optimal solution just by doing that. So if you have a pre-trained model with all the weights already optimized, transfer learning just means training the single last layer. So the second last layer, sorry. So you're just adjusting the weights there, which means it's very quick to do iterations. Yeah. What you can find is that, and this fast AI already provides this functionality, is you can tune the second last layer, and if you feel like you can squeeze out any more performance, you can actually unfreeze the rest of the layers and then actually optimize all the weights on all the layers to see if you can gain a bit more. But what you often find, especially with models which are already kind of very good at solving a particular problem, like image recognition, that images are made up of pixels together which produce patterns regardless of the image. If you have a really, really good image recognition model like ResNet 152 pre-trained, then you won't have to kind of adjust the weights. You'll end up with pretty good performance with just the second last layer.
Perfect. Yeah, it makes sense. I'm going to skip down to the next question from P. Wibberley. It's a question for you, actually, Saudamini. How did you realize the glass box explainability aspect of the model that you mentioned?
So I think one of the ways that you can do that, especially if you use the cat boost model, which is a gradient boosting algorithm, is using SHAP values. So this is a additional output that cat boost gives you, which basically tells you what was the percentage contribution of each individual feature to the forecasted number. So then it tells you exactly by what weight did each feature contribute to each individual forecast. So that way you can help make your model a lot more explainable. But that's obviously just for cat boost, but there are lots of different ways that you can do this. Like counterfactuals is another way where you can kind of compute a different variation of each feature and see what the impact is for of changing this feature to your model and give that impact as an output as well. So there are lots of different ways, but these are just two examples that you can use.
Thank you very much. That was a very popular question, actually. We've had a few upvotes on that one. So yeah, thanks for covering that off. We've got another question for you here, actually, Scott. Please explain list comprehension.
So the quickest way for a list comprehension is to basically simplify a for loop into one line and create a list that, if you're creating a list from a for loop, don't stop. You want to create a list from a list comprehension. So the pattern is you start a list, do something for I in, and you just really cuts it down. So that's the simplest way. You can have dictionary comprehensions as well, and the tuple comprehension. You can get comprehensions of all different things. Check it out, get into it, really good. Sorry, that's actually where we started when we said we were training people. That is where we started before we did anything. We started with list comprehensions.
Okay, fantastic, thanks. Question from Hasdeep. Hasdeep is asking, did you use Fast AI in Python or in another platform like Paperspace?
Yes, so when I initially started, I guess this is kind of more of a shout out towards Paperspace, because Paperspace does have a connection with Fast AI. So Fast AI is a free online course as well as a machine learning library. And essentially, when you're performing the course, they have the option to run the notebooks on Paperspace. Paperspace is a cloud service provider, and they provide free GPU for kind of a 6-hour limitation. So anyone looking to prototype, kind of get something up and running quickly and need access to GPU, for example, when you're doing neural networks, then I say go for Paperspace. And the cool thing is that they have these containers, these Docker containers, which are pre-set up environments essentially. So all you have to do is create a new notebook, select the Fast AI container, which already exists, and then you have all your libraries and all your modules pre-installed, and then you can get going. So again, really powerful way to utilize the libraries in PyTorch.
Okay, thank you very much. Next question. So normally we keep these things to about 2 o'clock. I'll keep things going just for another 5 minutes or so because we've got a couple of valid questions. So hopefully that's okay with you guys today because we started a little late. Next question is from Hui Feng. Images of the same item from different merchants can be shot very differently. E.g. the image of a bag could be held by a model. Did you implement an object detection before image classification in ResNet 152?
So one of the benefits of coming across this deep fashion data set is it had that variety already built in. So it had images of individual products on their own, images of products on models, images of products with amateur photos. And because we had that data set, this is a supervised problem, so everything was labeled. Naturally, the model will learn that regardless of whether you see a handbag being carried by a model or whether the handbag is on its own, then they still belong to the same class. Now, fortunately, from the results, we've been able to see that regardless of where it's modeled, because on e-commerce websites, you also get that variety, you get individual product and modeled images, the model's been able to successfully pick up the item of interest, which is the product. In a more kind of, again, more efficient solution, you might implement some image segmentation where you pull the product directly. At the end of the day, you're not really interested in everything else. But if your model can handle it, then it kind of saves you some work.
Fantastic, sounds good. That kind of actually leads a little bit in there. The question from Jason Mack, again, was directed at you, Kareem, and he was talking about the labels and categories for the image that you had. So essentially you did use that information to improve the model.
Yes, so again, we were quite lucky because, when you're attempting to derive similar images, more often than not, people will have to use the unsupervised method, which is, you don't have labels for images. Naturally, you won't unless someone's labeled it. And so you have a kind of a library of images and you want to determine which images look similar to one another. So you can attempt to cluster them and then attempt to label them in that way. So in that sense, you would use an unsupervised method like an autoencoder, for example. But because we had labeled images for products which were within the classes that we're interested, general products, jeans, handbags, shoes, for example, we use that to our advantage. So we train the model to attempt to classify our new product images. But by doing so, it became very good at naturally clustering similar looking products, because those similar looking products will inevitably be classified as the same class. And I think, we gained some really good results, specifically also around outfits, different outfits where you have a different jacket, jeans, and a shirt, for example. If you feed that in, it actually finds images where people are wearing similar outfits, but different product types. So that just kind of gave some evidence that it was actually doing quite well.
Fantastic. I wouldn't go on, Scott, sorry.
So I was kind of just adding to that as well, on the sort of scraping side and getting the data. One of the beauties of bringing these images down, we pulled the descriptions down and the brand names down as well, then use list comprehensions to break that down. So then we have like a description, we have a color, we have a pattern. And so we could actually build up a labeled data set from just scraping it down from the web, which is absolutely great.
Perfect. That's fantastic. That kind of answers Andrew Thornton's question there at the bottom as well, talking about taking the labels directly from the website. So that's cool. Just a couple of questions left there, actually. We'll go for Alok's question first. Hopefully this makes sense to you guys. Should the embedding vector also include the tabular data, season, price, brand? So works as a multi-model one.
Yeah, could do. So this is also leading on to what Scott said. We're pulling all the attributes associated with the models. In essence, those attributes carry a huge amount of value relative to the image, the similar image. So if you were actually going to implement this for a client as a commercial solution, to reduce the risk associated with comparing dissimilar products, what you would do is you would allow the model to bring together similar looking products, but then you would use your attributes to filter that down so it was actually bringing together relevant products. So you might use the material or the pattern or the product type as a start, to ensure that what you're comparing is actually relevant. And then if you did some sort of analysis using the price, or you're attempting to do forecasting, you would know naturally that you're dealing with actual similar products, and you're basically attempting to remove any error associated with the model. So it's really beneficial to have the attributes.
Fantastic. And we've done well here, actually. We've blitzed through some questions. So we've got one final question. Why did you use ResNet 125 instead of VGG16 or AlexNet or another model?
So I actually saw this question before. You mentioned that I didn't actually do a sensitivity study. So in reality, if you're working in a commercial environment, you wouldn't just choose one model. I didn't do much hyperparameter tuning as well. So in reality, you'd build this enormous pipeline which could feed in your different models and your different hyperparameter tuning modules, and then you would do a huge sensitivity to understand which produces the best results. But just because it was so easy using FastAI to import ResNet pre-trained, that's what I went for.
Makes sense. Okay, we've done really well there, guys, to blitz through those questions. So yeah, thank you for your time. As I mentioned just before we started the questions, really enjoyed the format today, getting you guys involved. Hopefully you've enjoyed being part of it. We had a good number of attendees, good number of questions. So I think it was well enjoyed by the community, and I've seen a few comments come through already. So thank you very much for your time, and yeah, hope you've enjoyed yourselves.
So it's
Thanks very much.
Great.